Chapter 11.2 Randomized Block ANOVA, examining the effect of a single factor by blocking a second factor. In the previous section, the order in which the smartphone satisfaction score were presented had no bearing on the result. For example, if we rearrange the BlackBerry score from 66, 74, 79 to 74, 79, 66 in the third column or table 11.2, the ANOVA result would be unchanged. However, there are situations where the order in which the data are presented does have an impact on the analysis. Consider the following example. Tony is an area manager for Procter & Gamble, or P&G, a company that provides a variety of household products sold at many retail stores. Tony is responsible for 3 P&G representatives who make sales calls to store managers to service their product needs. Table 11.15 shows the number of sales calls the 3 reps made last week for each weekdays. The data can also be found in the Excel file sales.xlsx. Tony would like to know if there is a difference in the average number of calls made per day by these 3 sales reps. At first glance, this appears to be a straightforward one-way ANOVA problem like we saw in the previous section. However, we are comparing average score for each phone. Here, we will compare average sale for each representative. Let's perform a one-way ANOVA with Excel using alpha equal to 0.5. The results are shown in figure 11.10. According to figure 11.10, the average 5 calls per day, Amy average 7 calls per day, and Beth average 5.4 calls per day. Because p-value and cell F12 equal to 0.126, which is more than alpha equal to 0.05, we fail to reject the null hypothesis using one-way ANOVA. Tony concludes that, based on the data from these 3 samples, there is no difference in the average number of sales calls made per day by these 3 reps. However, I hope you see the coming. The order in which the sales calls have been recorded is important and has meaning because each value represents a different day of the week. The first row of data in table 11.15 is linked together because it represents the number of sales calls made on Monday by each employee. The same logic holds true for the other 4 rows. For example, if we rearrange the order of Dan's sales call, we would also have to do the same for Amy and Beth's sales call to ensure the proper data value is assigned to the proper weekdays. This dependency across the row is analogous to the situation from chapter 10 in which 2 samples were matched pair. When we have this kind of structure with more than 2 populations, the appropriate procedure to test the difference in population mean is known as a randomized block ANOVA. With a randomized block ANOVA, we have added a second factor to the procedure. The main factor is the sales rep, of which there are 3 levels, Dan, Amy, and Beth. Tony would like to determine if this main factor has an effect on the average sale of sales calls made per week. However, by arranging the data according to weekdays, we have introduced a second factor. which is known as the blocking factors. The level of the blocking factors for specific weekdays are known as blocks. The purpose of the blocking factors is to remove some of the variability in the sales calls associated with the weekdays, which may allow us to better detect any differences due to the main factor, the sales rep. This is what we are truly interested in knowing. For example, if the average number of calls on Friday is less than Monday's average, perhaps one or more of the reps begin the weekend early. A randomized block ANOVA might do a better job at detecting a difference in the average number of calls made by the 3 employees than a one-way ANOVA. Let's give it a try. Step 1. Identify the null and alternative hypothesis. The hypothesis statement for a randomized block ANOVA is identical to that for one-way case discussed in the previous section. Null hypothesis, M1 equal to M2 equal to M3. Alternative hypothesis, not all M's are equal. For this example, I'll set the probability of making a type 1 error to alpha equal to 0.05. Step 2. Calculate the factors mean, the blocks mean, and the grand mean X double bar. The mean calculation for our sales call data from table 11.15 are shown in table 11.16. Notice that I calculated the mean for both the column, the factor or sales rep, and the row, the block or weekdays. Once again, we need to find out our grand mean, X double bar, which is the sum of all the data divided by the total number of data points, or NT. In table 11.16, this represents the overall average number of sales calls made per day by these 3 reps. So X double bar is equal to 5.8. Step 3. Calculate the total sum of square, or SST. The sum of square, or SST, for a randomized block ANOVA is calculated the same way as it is for one-way ANOVA. We'll again use equation 11.2 to determine the SST with the help from the calculation in table 11.17. Before we move on to the next step in a randomized block ANOVA, this would be a good time to stop and catch our breath with a your turn exercise. This one will give you an opportunity to start a randomized block ANOVA problem and learn about mystery shopping at the same time. Step 4. Partition the total sum of square, or SST, into sum of square between, or SSB, and the sum of square block, SSBL, and then the sum of square error, or SSE. The total sum of square, or SST, for the randomized block ANOVA is partitioned into the following 3 sum square. 1. Sum of square between, or SSB. 2. Sum of square block, or SSBL. And 3. Sum of square error, or SSE. Equation 11.12 shows the relationship between these sum of squares. The sum of square between SSB, which is found using equation 11.5, has the same meaning as it does for a one-way ANOVA. For our sales call example, we have already determined that X double bar is equal to 5.8 and K equal 3. Table 11.16 provides us with the remaining sample data needed for this equation. For your convenience, Table 11.18 summarizes this information. Applying this data to equation 11.5, we have the following. SSB is equal to 11.2. The mean square between MSB is again found using equation 11.6. MSB is equal to SSB divided by K minus 1 equal to 11.2 divided by 3 minus 1 is equal to 5.6. Next, we will see that equation 11.13 introduces the sum of square block, or SSBL, which measure the variation between the block mean and the grand means. Where SSBL is the sum of square block, Xi is the sample mean from the ith block, X the grand mean, X double bar is the grand mean for all the data values, B is the number of block, K is the number of population being compared. Remember, for our sales call example, the block are the weekdays, which mean that B equal to 5. Table 11.19 summarizes the data shown in Table 11.16 that is needed for equation 11.13. Applying this data to equation 11.5, we have the following. SSBL is equal to 20.4. The mean square block MSBL is found using equation 11.14. Using our sales call result, we have the following. MSBL equal to SSBL divided by B minus 1 equal to 20.4 divided by 5 minus 1 equal to 5.1. The mean square block MSBL represents the variance associated with the sum of square block. If the average number of sales call per day was the same for each weekdays, the mean square block or MSBL value would be 0. The last component of the total sum of square or SST is the sum of square error or SSE, which represent the random variation in the sales call data that is attributed to neither the employee nor the weekdays. The SSE can be determined using equation 11.15. Using our previous result, we have the following. SST equal to SST minus SSB minus SSBL. So SSE equal to 38.4 minus 11.2 minus 20.4 is equal to 6.8. Finally, the mean square error, or MSE, represents the variance associated with the SSE and can be found using equation 11.16. Using our sales call result, we have the following. MSE equal to SSE divided by B minus 1 times K minus 1 equal to 6.8 divided by 5.1, 5 minus 1 times 3 minus 1 equal to 0.85. Now that we have partitioned the SSE into its three components and calculated the mean square, we are ready for the test statistic. Step 5. Calculate the main factor test statistic. The main factor test statistic for a randomized block ANOVA is used to determine if a difference in population mean exists. It is shown in equation 11.17. Using our mean square values from the previous step, the calculated F-score or Fx is calculated as follows. Fx is equal to MSB divided by MSE equal to 5.6 divided by 0.85 equal to 6.59. Step 6. Determine the appropriate critical value. The main factor test statistics shown in equation 11.70 follows the F distribution with the following degrees of freedom. D1 is equal to K minus 1, D2 is B minus 1 times K minus 1. Using our P&G sales call data, the degree of freedom are as follows. D1 is K minus 1 equal to 3 minus 1 equal to 2. D2, B minus 1 times K minus 1 is equal to 5 minus 1 times 3 minus 1 equal to 8. According to table 11.8, the critical value for our sales call ANOVA using alpha equal to 0.05 and degree of freedom equal to 2 and 8 is F alpha equal to 4.459. We can also obtain this critical F score using Excel f.inv.rt function as follows. Step 7. Compare the F test statistic or Fx with the critical F score or F alpha. Because Fx equal to 6.59, which is greater than F alpha 4.459, we reject the null hypothesis according to the decision rule shown back in table 11.9. We can see this graphical in figure 11.11. Step 8. State your conclusion. By rejecting the null hypothesis, we can conclude that not all of the three population mean are equal. Tony can conclude that some employees average more sales per day, more sales calls per week than others.